Yeah, just a couple of quick things. Today's schedule is a little different. We will have, after this talk, we'll have morning coffee, and then one more talk this morning, then lunch at Churchill College as usual. The afternoon is completely free, and then this evening is the formal dinner it's at drinks at 7:30, dinner at 8 o'clock, and that is at Caius and Gonville College, which is one of the old colleges in the city center on the other side of the river. You'll have to look at a map to find your way there. There's a certain amount of alcohol is included in the event, so just so you're prepared for that. The other thing is that beware, tomorrow morning is forecast very likely chance of rain, so bring your umbrellas or whatever. Okay, thanks.
So the second talk is then by Oliver Roendigs, who will speak on various active hermitian cases.
Thank you very much. I'd like to thank the organizers for allowing me to make an advertisement here. This is what I consider my talk. It's an advertisement for a specific P1 spectrum. It's available on the archive. It's joint work with Alexey, Ananyevskiy, and Arne Ostvaer. So the setup is as follows. I'll take a field and characteristic of this field should be not 2, because we'll deal with quadratic forms. And the easy way. And SH of F is the P1 stable or motivic homotopy category of F. As constructed by Morel and Wołodzki. And in this category there's a motivic spectrum which was first constructed by Jens Hornbostel, which represents Karoubi's Hermitian K groups. Let me write this down. And I apologize to anyone who thinks this notation is really awkward. I don't write it as KO but as KQ in order to distinguish it from the topological KO, which will come up in this talk. So you can think of this Q as standing for quadratic. So if you want to know how the spectrum looks like, if I sort of the construction given by Jens Hornbostel, and which also uses work of Marco Schlichting, as a P1 spectrum, it can be described as follows. There's sort of a presheaf of S1 spectra by sort of a K-theory construction on the category of, say, vector bundles over the schemes with duality for KO, and there's a forgetful map to the ordinary algebraic K-theory presheaf as defined by Quillen, and there's a fiber of there's a map in the different direction, sort of the hyperbolic map. You can take the fiber of that, and this gives you for sort of anti-symmetric bilinear forms some presheaf USP, and then there's KSP, and then there's UO, and then it's periodic from there. And in order to describe these structure maps, one uses Karoubi's fundamental theorem relating these these fibers of the forgetful and the hyperbolic map. But there's a more geometric construction of the spectrum as an HP1 spectrum. So this is a 4-2 sphere, or should I start with this here? Sort of to connect it with Jeremiah Heller's talk. You take the étal classifying space for the orthogonal group, and you take the étal classifying space for the symplectic group, and then it's periodic from there. So you can see what you get is an 8-4 periodic spectrum. Yeah, and the very effective Hermitian K-theory spectrum will be a certain cover of this spectrum KQ. And in fact, I will define sort of 3 ways of taking covers in this category, and then we'll hopefully choose the right one. Okay, and since I mentioned this is going to be an advertisement talk, I would like to give you some reasons, I think at least 5 reasons, why this specific cover is the right one. As with advertisements, you are entitled to believe these reasons, or, well, maybe, no, I should not continue this sentence. So, there's a related and simpler spectrum, which is algebraic K-theory as defined by Blavatsky. So this represents Quillen's algebraic K groups on the category of smooth F varieties. So this here has a P1 spectrum. As you can see, is 2-1 periodic. The structure map is given by sort of product with the difference of the trivial and the tautological line bundle on P1.
Everything's the same in that sequence? Is that right?
Here, everything's the same. Yes. Okay. And what else do I need? Right. I need, of course, the first algebraic Hopf map. So its construction is as the canonical map from A2 minus 0 to P1, and sort of regarding these degree conventions, this would be a map which is in the 1-1 homotopy group of the sphere spectrum. Alright, I didn't introduce the sphere spectrum. Sorry about that. So this is the infinite P1 suspension spectrum of the spectrum of the base field with a disjoint space point. And this name is, well, due to the fact that it's the unit of the smash product in this category. And I'd like to confuse you slightly by mentioning that there are different indexing conventions. So this here would refer to the weight and this here to the simplicial dimension, but there are people in this area who would write this as 0 plus 1 times alpha. And not too long ago, a preprint appeared on the archive by John Greenlees, where he strongly argues that one should not write alpha, but instead sigma, at least from an equivariant perspective. I hope I'm quoting you correctly. Yeah. So I might switch between these conventions. Let's see.
So alpha and sigma both mean the sign representation.
So the sigma refers to the sign representation.
What if
And-
you're doing motivic equivariant homotopy theory? What if you start doing C2?
I'm not going to do that.
Won't sigma cause a problem in the future?
Sure. Yeah. Sure. Can I leave this on the board, nevertheless? This talk is recorded anyhow. It's too late. I said it. Yeah. Okay, and sort of the main theorem that is going to be used is an analog of Wood's co-fiber sequence relating complex and real K-theory. You have multiplication with eta on this Hermitian K-theory spectrum. So this gives you a map. Maybe where's an eraser? Let me write a bit larger. So as I said, there's a forgetful map to algebraic K-theory, and then there's a connecting map, and this can be described explicitly. So KGL is the same as its 2-1 suspension. So this is Watt periodicity, and this map here is the 2-1 suspension of the hyperbolic map. And this here is a co-fiber sequence. This will be the main input. So let me now define these three filtrations. First one, Blavatsky's slice filtration. The definition is as follows. You consider the localizing full subcategory of effective spectra, effective P1 spectra. So this is contained in here. So this is generated by suspension spectra of smooth schemes. And it's a triangulated subcategory. Okay, and you can sort of, this inclusion has a right adjoint, and now sort of to complete the filtration, you can move this subcategory around by taking suspensions. Let me suspend Q times, where Q is an integer, and then I would adjust this here appropriately, and then I get an inclusion IQ having a right adjoint RQ, and this gives the filtration. So FQ is defined as IQ composed with RQ, and we have an FQ plus 1, and this continues sort of infinitely in both directions, but if we take the co-limit, then Q goes to minus infinity of this FQ, we actually get the identity, and the co-fiber of this here, this is the Qth slice. And just to give you two concrete examples.
So when you say localizing, you don't allow desuspensions?
Oh, I allow these suspensions. So this is a triangulated subcategory.
But only like the S10 desuspensions.
The S10 desuspension. Yes. Maybe I'm not using the correct adjective. So
I'm happy.
okay. So in fact, these are all triangulated functors, which can be very convenient. So this is a pro of this filtration. This filtration has a contra, or several maybe. Sort of, if I take the limit here, q going to infinity, this is non-trivial. And yeah, it behaves badly in general with respect to connectivity. So this will be the second filtration that I'll introduce. Any further questions? Am I too slow? I think I'm too slow. But just slow me down. It's very welcome. Let me attribute the computation of the slices of K-theory to Mark Levine and also Vladimir Roendigs. So the zero slice of KGL, this is the Roendigs motivic Arne with length spectrum representing motivic cohomology on smooth schemes over F. And in fact, the whole graded slice of KGL you can think of as a polynomial ring in the Bott element where the degree is 2, 1. Yeah, and one other nice thing, the slice spectral sequence is strongly convergent. Okay, that's this, and let me give you another example for this hermitian K-theory. So the zero slice of hermitian K-theory is a bit bigger. In fact, infinitely many summons, one integral, and then mod 2 motivic cohomology. And I can also give you the graded slice. This is close to being a polynomial ring on an element which I call square root of alpha, which is another instance of bad notation, but I have a reason for this bad notation. So there are relations, 2 times eta is 0, and then it's not really quite polynomial, there's something weird happening. Eta squared maps non-trivially to the square root of alpha. So square root of alpha has degree 4, 2, and when you multiply it with itself, you get an element in degree 8, 4, and this corresponds to the 8, 4 periodicity that you see in the spectrum. And this is the reason for this bad notation. And yeah, the degree of eta is 1, 1. Okay, let me erase something here.
Hey, Oliver, what do you mean when you say eta squared maps to square root of alpha? What?
Yeah, I've been waiting for this question. Yeah.
You're welcome.
Thanks a lot. Let me mention that, I mean, we had a very short conversation this morning, but it was not about this question, right?
That's right.
You were not primed to ask this question. So thank you very much. What is happening here? So this eta, it generates, for example, something in the one slice. So I can multiply the one slice with the one slice, and this should map to the two slice. well, it maps to the two slice, sorry. So inside of here you have the summand generated by eta, which is a 1-1 suspension of this guy here, and there's another 1-1 suspension of this guy, so this is somehow contained in here, and this has the following form. Actually, okay, let me change this slightly. Let me smash over the zero slice of the sphere spectrum, which is just mz, and then this here becomes a 2-2 suspension of mz mod 2 and a 3-2 suspension of mz mod 2. Yeah, you can think of this here as being a Bockstein. So this here contains, among other things, a 4-2 suspension of integral motivic homology. Yeah, so this here is this eta, this is square root of alpha, and you get a map here, and this here can only map trivially here, but this maps non-trivially via the connecting map. And this is what this relation here means. And yeah, I don't know whether there's sort of a more canonical term for this type of multiplication. Okay, this answers your question, I hope.
Yes, thank you.
Okay, so the next filtration that is coming up is Morel's homotopy T structure, and it sort of mimics the usual Postnikov filtration on the homotopy categories. So here's one way to define it. You take the stable homotopy category and then you look at the D connective motivic spectra, where again D is an integer, and this here is generated under homotopy co-limits and extensions by the following suspension spectra. D plus star sigma x plus, where x is a smooth F variety. So you think of these as being D-connective, and there's a different characterization in terms of the homotopy sheaves. Yeah, so motivic spectrum is D-connective precisely if the homotopy sheaves in degree less than D, yeah, the simplicial degree, vanish. Yeah, so these are D-connective. Yeah, here's an example. If you take the qth effective cover of KGL, this is Q-connective. So this holds for any Q. But if you take, for example, the zero slice, the zero effective cover of KQ, I mean, you can guess it from the description of the zero slice here. This is, how should I phrase this? Is not Q-connective. And this is also for any Q. So this is what I mentioned before. This slice filtration does not behave well with respect to connectivity. And I can, if you like, I can make this more explicit. So if we look at some integer less than 0 and we take pi 4k, 0 of the zeroth effective cover, so this here corresponds to this here, so this is the same as this here by definition, and if k is less than 0, we are in a range where this here corresponds to Witt groups. And there you can see that this is not connected.
KQ isn't Q connective either. So
Pardon?
the KQ wasn't Q connective to begin with.
Yeah, but I mean, the KGL isn't Q connective as well. Or would you not agree? Okay.
Yeah.
Let's see. Oh, I am too slow. Okay, so the third filtration, which is due to Spitzweg and Ostvaer, and this is the very effective filtration. Yeah, I should mention. So this here is generated under homotopy colimits and extensions, but no simplicial desuspensions. And this is also true in the following case. Sort of the very effective subcategory, the full subcategory generated under homotopy colimits and extensions by suspension spectra of smooth schemes. Yeah, and this is again a category you can sort of shift around. So Q-fold P1 suspension, then I have an inclusion which is sort of the very effective inclusion, and we have a very effective retraction, and then we get a very effective slice filtration. And this filtration is better in the sense that sort of here again you recover the spectrum, so the colimit of these is the identity, but the homotopy limit here vanishes because by construction the Qth effective cover of E is Q connective.
What's the difference? You sort of the difference between the effective and very effective?
Sort of this here is a triangulated subcategory, and this here is not. Yeah, so this means that slices are easier to compute, but the very effective slices are not so easy to.
Very effective. What is that category closed under? It's not triangulated, but you said it's closed.
Closed under homotopy colimits and extensions.
Extensions means what exactly?
So if you have a cofiber sequence and the two outer terms are in this category, then the middle term also is. In fact, I think Tom Bachmann he wrote down an argument that this here is actually not necessary. But let me just keep it like this. Okay. And in fact, Tom Bachmann has the following very nice characterization of this very effective filtration, which works over a perfect field. So the very effective cover of E corresponds to the effective cover of the connective cover for all Q and E. So there's sort of no need for this definition, but this is how it was first defined. Yeah. And now let me define the spectrum that I want to advertise. This following standard convention. This is little kq, so this is the 0th very effective cover of uppercase kq, And of course, we do the same for algebraic K-theory. And should I use this blackboard? Maybe just a little. So here's the fact. The very effective cover for algebraic K-theory is in fact the effective cover, and you can think of this as being a reason for this strong convergence property that I mentioned earlier. And let me just sketch an argument which works in characteristic 0, but there's also an argument in positive characteristic. Don't worry about that. So this proof would start with the observation that if we take the cofiber of the unit map for MGL, that this here is contained in the first very effective subcategory. And this is a geometric argument using these Grassmannians that are used to construct the spectrum and the Morel-Wołodzki homotopy purity theorem. So sort of, I mean, you can think of this here, as we've seen in Mark Hoyas' talk, as sort of a tone spectrum for a point, sort of, and this here is tone spectrum for the general linear group. You can approximate this sort of using finite Grassmannians, and then you can take this point here and basically enlarge it to an open affine subscheme in a Grassmannian, and with the homotopy purity theorem you can then deduce a certain very effectivity of the cofiber. Okay, maybe I should say homotopy purity and some geometry of Grassmannians. Okay, and now there's a description of algebraic K-theory as, I should say, the algebraic Borgesian spectrum receives a map from the Lazar ring, and we can describe algebraic K-theory as the following construction. So you quotient out the generators of the Lazar ring x2, x3, and so on, and you invert x1. And this then tells you that the zeroth effective cover is gotten as the following quotient, where you don't invert x1. And I mean, MGL, I didn't say this. So this here is by definition very effective. This here tells you that also MGL is very effective. And in fact, this helps you to sort of describe the whole effective and very effective filtration of MGL. They coincide. So here, this here is very effective, and then when you take these homotopy co-limits, it remains very effective. So this is one argument. Here. Okay.
Can you also argue that MGL is very effective because it's connective and effective?
Yeah, you can argue like that as well. There's one thing I'm sort of, I mean, this definition of the very effective filtration, this works over any base scheme, and the very effectivity of MGL holds over any base scheme. This homotopy T structure, of course, it also exists, but characterizing it using vanishing of homotopy sheaves, this is unclear if the base is not a field. And of
Check connectivity up. Sorry, you can check connectivity up the pullback to here.
right, yeah.
When you call a motivic spectrum very effective, what do you mean?
Pardon?
What do you mean when you say that something is very effective?
That it's in this subcategory for Q being 0. So it's generated under homotopy colimits and extensions by P1 suspension spectra of smooth schemes. Okay, of course, another reason for giving this argument is the following corollary. If you take the complex realization of little kgl, you get little ku. Because, it's easy to see that MGL realizes to mu, and we have this description for ku. Okay, what do I want to do now? Okay, let me remind you of the following. So we have this bot element, and it multiplies on the periodic algebraic K-theory spectrum, but then sort of by universal property also on the very effective cover. And due to the periodicity, this here corresponds to, okay, let me write it like this. So this is the P1 suspension of the 0th very effective cover of KGL, but this here, no, the effective cover, sorry. Of course it's true either way, but this here is the same then as the first effective cover of this here, which is by Bott periodicity the first effective cover of just KGL. So if we take the co-fiber here, this is just the 0 slice of KGL, which is motivic cohomology. Yeah, so we have here Bott periodicity, we have a certain map here, and then we get a connecting map. No, 3, 1. Okay, and we have the following lemma. So you smash these maps suitably with mod 2 motivic cohomology. Yeah, so first let's take delta, then we land here. And then we take gamma, and then we land here. And this map can be described as multiplication with the first Milnor operation. And this is sort of straightforward to see then again by realization, so by a topological argument. Once you know that the Steenrod algebra is invariant under extension of base fields. Okay, so you have sort of a handle on the motivic cohomology and motivic homology with mod 2 coefficients of this little KGL. Now, sort of this wood co-fiber sequence that I mentioned in the beginning, I mean, this was also known to Bachmann. This also induces a co-fiber sequence for the very effective versions. So you can multiply with eta here, and then the co-fiber is little kgl, and then you get your map here. Yeah, and these are induced by the forgetful and the hyperbolic maps as before. Basically, this can be shown using the uppercase case, and then some sort of properties of this very effective slice filtration, its characterization in terms of homotopy sheaves, and then the following fact, which was proven by Tom Bachmann, that the -first very effective slice of KQ, that this actually vanishes. So what we get from that, this is reason one. Why this here is a good analog of connective real topological K-theory. And from this here we immediately get reason 2, which is when you take complex realization of little kq, you get little ko. And I guess at least for some of you this might then be actually a convincing reason. If this wasn't true, well, I shouldn't have given this talk at all, I guess. At least not for this audience. Do we have here? Okay, yeah, I mean this is not needed anymore. Yeah, and as Bert Guillou told me, if you think of your base field to be the field of real numbers, and you take a corresponding equivariant realization, then of course you also get some version of equivariant real connective K-theory. I don't know whether I said the word in the correct order, but it's the one that appears in a preprint by Guillou, Hill, Isaacson, and Ravenel. And John Greenlees has a sort of an article on connective real and complex topological K-theories, where sort of several desirable properties are listed. So
when you said connective real, so real is arterial, equivariant real, the real is the arterial real, and the equivariant is for which group?
I shouldn't have said these adjectives, I know. So what is your question?
For C2.
That's for C2.
So the group that acts, is it the product or is it C4 with the augmentation? It's really C2 times C2, and one is the augmentation factor, the real factor, and the other is the equivariant factor?
No, the real is sort of real K-theory.
I know.
Yeah. But not artia real, not uppercase real, but lowercase real. And it's just C2 that is acting. No C4. Is that correct? It's correct, right?
Yeah.
C2
There are
equivariant
three authors.
real in the sense of lower real.
C2 KO.
No, I can't hear whether it's a capital or a lowercase.
Say what?
We have to fix that.
Okay. Let's see. What else do I want to? I have 3 more reasons to give, and I can use this co-fiber sequence also for the following corollary, which is as follows: you take KGL, smash it with Z mod 2, then you have the map going to the 2-1 suspension of KQ, smash that with MC mod 2, and then you go back to KGL with the forgetful map, smash MC mod 2, and then you can check that this is multiplication with square 2, and this has the nice consequence that the mod 2 motivic cohomology of this little KQ corresponds to A mod A of 1, the sub-algebra generated by square 1 and square 2, so you can get started with your Adams spectral sequence computations over any field of characteristic not 2. And computations have been made in several cases already, for example for the reals and the complex numbers. Is this a reason? Yeah, this is a reason. Okay. So what one can also compute, and this is actually not that hard, is the slices of this little KQ. Of course, the very effective slices were computed by Tom Bachmann, and they follow very closely the topological story. So you have the same generators as before, but you do not invert the square root of alpha. You also have the same relations. And if you like, you can go ahead and try to compute with this slice spectral sequence. So we can try to compute pi star minus n of little kq. Let me just draw a little bit of this picture, maybe introduce notation first. HSW is an abbreviation for the integral motivic cohomology of f, and lowercase HSW is an abbreviation for the mod 2 case. These are the only ones that appear in these slices. And then we get an E1 page which looks as follows. So we only have slices in non-negative degrees. So this is the slice, and here we have pi minus n and pi minus n plus 1 minus n, and so on. And this looks as follows. You have h and n, h n plus 1, n plus 1. This is a lowercase, so it's mod 2. N plus 2, n plus 2, n plus 3, n plus 3. And this column looks like the associated graded of the Milnor-Witt K-theory of that field, and it is. So this is reason 4. Pi 0 minus star sigma of little kq. This is isomorphic to the Milnor-Witt K-theory of the field. Yeah, I have the minus sign. Okay, the next column starts with integral hn minus 1 n, and then you have this here. You have this here. And let me also give you this here. How much time do I have? Okay. Did I start at 10 sharp or? Okay. Is there a mistake? No, not yet. So there's the next integral group coming up, but then it's mod 2 groups from there on. And one can also compute the first slice differential. And we have the following neat thing. There's a sort of projection to mod 2 followed by multiplication with tau, which goes here, and this continues all the way, and this will wipe out this column here. But we also have, so this is basically multiplication with tau, but we also have square 2, which goes here, and this is first projection to mod 2 and then square 2. And this is the first differential. The only option you can have of a second differential is from here to there, and then you have to do a bit of work to check that this is actually 0. So you get that E2 is E infinity 4 pi 1 plus star sigma little kq. And maybe just because there are so entertaining groups coming up, let me be a bit more explicit. Oh no. Oh wait. Let me erase this here. So we have a 3-stage filtration of this group, pi 1 minus star sigma little kq, which surjects onto h star minus 1 star. And here we sort of have the first part, which surjects onto h star star plus 1 mod square 2 of an integral group. And the second part coincides with this here, star plus 1, star plus 2, modulo square 2. So this is the filtration, and you can think of this here as being generated by the topological Hopf map. And then it's easy to check how multiplication with eta operates in the slice spectral sequence, because you just sort of walk up here, so it's projection integral to mod 2 on this first stage, and then it's just an identity on the other stages. So this here is given by eta times eta top, and you can see already that this is not split as a short exact sequence of modules over Milnor-Witt K-theory. I mean, yeah. But it's not even split as a sequence of abelian groups when you pick your favorite degree, which is going to be 2. Because in this case you have here K3 indecomposable, and then here you have pi 1 minus 2 sigma little kq. And let me just restrict to the case of the rational numbers, because in that case this here is gone. Yeah, this is just a z mod 2, and it is killed by multiplication with rho squared, which is what square 2 is really. So you only have this short exact sequence where this here is then this here is 0 in this case, so you have an H2 3. Okay, and this is not split as a sequence of abelian groups, because you can map here to the corresponding sequence for KGL. So this here is the identity. We get a map here, and here this is the third Milnor K theory, which for the rational numbers is just z mod 2, and for the rational numbers this is just z mod 24, and this is z mod 48. And okay, I have time for this anecdote. My first visit at this Isaac Newton Institute was in 2002, and when I visited the restroom at one occasion, I saw a graffiti on the wall which was K3 of the integers is Z2 times Z mod 24. Yeah. True story, I didn't make this up. Okay, so here you can see that this extension is in general non-trivial. I have to give you the fifth reason. Do I have time for that? just want to state one theorem, collaboration with Markus Spitzweg and Arne Ostvaer. You have this unit map from the sphere to little kq. This induces the following sequence. You have k Milnor star, no, 2 minus star, not 24. Then you have the first homotopy groups of motivic spheres, and then you have little kq. And this is exact if the characteristic of the field is 0 and is exact after inverting the characteristic if it is odd. So you can think of the unit map from the sphere spectrum to little kq as being a one connective map. And now I cannot say just as in topology because it is two connective, and it is not going to be two connective because there's a beautiful theorem due to Ananyevskiy, Levine, and Panin, which says that in certain ranges this here is always torsion, but pi 2 plus 2 sigma of little kq is the zeroth symplectic k group of the field, which is not a torsion group, which is the integers. Yeah? So it's this unit map here is one connective, not two connective. Thank you.
The questions? Isn't
So if the moral of the story was that the very connected slices are the way to go, why were you computing homotopy here with the slice spectrum?
Yeah, that's a good question. And for example, Jonas Killing and Hakon Kolderup, they made computations with the very effective slice spectral sequence already. And you can ask Jonas about these computations. It's possible. Yeah. But in the case of the effective slice filtration, I mean, we sort of knew the differentials precisely. The first differential.
Do you know anything about the species of the spectrum we looked at here?
I would desperately like to know more about the spaces. Sorry.
This formula for the slices of little kq up there, it bothers me a little bit because I would expect that when you take the square root of alpha and you square it, you get like 4 times the generator rather than the generator.
Yeah, but it does not seem to happen.
That arises in the spectral sequence because square root of alpha will support some differentials, and so it won't survive the spectral sequence.
So it's like d1 squared itself. Okay, all right.
Yeah, I mean, this here is the square root of alpha term, and there's this multiplication by first the projection and then multiplication by tau. So the kernel here is in fact 2 times this group, and this is where you get this.
Yeah. I'm happy now.
Okay.
Do you know anything about the very effective slices of the sphere?
Well, Tom Bachmann computed the 0th very effective slice of the sphere, which is the same as the very effective slice of kq, which it's an extension. You can write it as an extension in 2 different ways. Integral with motivic cohomology. I don't know what the status of the higher ones is.
Well, I mean, you can compute the first one from your theorem about pi 1. I mean, one would obviously like to go the other way around, but I don't know how to do that. And then one might think that the second one should be 0, because like pi 4 and pi 5 are 0 classically, but that's false. So I don't know.
questions?
And let's thank Oliver again.